Okay, so good morning. Today we will go to two dimensions. So just as a quick reminder, we have done first just one differential equation. So first order differential equation, nonlinear. And we have studied then one-dimensional systems. We have found their fixed points and therefore establish the stability of the system if it goes to this equilibrium point, which is an attractor, or if it goes away from this one, which is a repeller, and so on. Last class it was very interesting because we introduced the concept of bifurcations, which meant systems where you just change a parameter and suddenly something in terms of the structural representation of the system in terms of fixed points completely changes. So some fixed points, they show up, they disappear, or they change the role from an attractor to a repeller, or vice versa. So there was bifurcations in one dimension. Now today we are entering the world of two dimensions. And this is somehow a big step because now we will consider two differential equations. But in order to enter in a smooth way, not hurry up too much, we will enter in the world of linear systems as well. Okay? So in the next class, we will see how two dimensions can be analyzed when systems are non-linear. But right now, we will consider linear systems. Okay, just a quick motivation. Why to go to two dimensions? So last time we were actually studying the population, you remember, of the budworms, and we have the budworms were expressed with the letter X, but we also had these predators, which were the birds, and we somehow, in order to introduce the effect of the predators on the birds, we have to have a very simple relation like this, X, and this is P. Well, I think this was actually N. Well, it doesn't. If you go back to the slide, and then we had this relation, if you remember well. So it start from 0 and then grows, which meant that there is a very restricted relation between predators and the number of budworms. So we cannot have something that is more complicated than that. However, right now, if we go to two dimensions, we will be able to have like a more interesting model. So we still have the same axis. So we have N, P, but now we can somehow consider as this kind of evolution if we wanted. Okay, this cannot be done in a one-dimensional system. In a one-dimensional system, we will have just this line, so the particle will just follow this flow. In here, we can have this flow as well, but of course, this is too restrictive because what happens if you have a condition like this? So, in a phase plane, in a two-dimensional domain, you will have like a two-dimensional plane full of trajectories, and that will make the two-dimensional description very rich. Okay, so this is like the motivation. Okay, so we are in the world of linear systems right now, and this is representative of a linear system. Okay, a system of the type AX. So this is some coefficients representing how the number of the individuals in the population, if we think, for example, in the previous slide, is associated with the rate of change of X and Y. Okay, now these coefficients A, B, C, D, they can be introduced in a matrix. In this example, 2 times 2, because we have just two equations, and the vector X, so we here in bold notation, is just XY. Okay, but let's remember what linearity means, a linear system means. So in this equation we have two different somehow mathematical terms. We have the differential operator, and the right hand side is like an algebraic function of x and y. Here there is no differential operators. So we can have a differential equation being linear if both differential operator and this function f are linear. Okay, so it means that the superposition principle applies, and we can have a differential operator expressed like this and a function expressed like this. If this can be done, we can say we have a linear differential equation. So in order to go right now beyond, we need to introduce the concept of phase plane. Now we have seen phase plane, or let's say these phase portraits before, but they were just like one-dimensional representations. Now we have actual two-dimension. Okay, so before a particle was allowed to just somehow move along a given line. So it was, the slide was called, the session was called flows on the line. Right now the particles are allowed to move everywhere within this two-dimensional plane, and this is going to be called then the phase plane. So let's start with a very interesting equation, which is also everywhere in engineering. This is the spring damp system. So you can recognize in here that we have a second order differential equation. Already this gives us a hint that we will be able to, or we will have to express this equation as two ODEs of first order each. Okay, in here we can think about x as position, s dot as velocity, and x dot dot as acceleration. Okay, but since we have just two dimensions, we actually need only two somehow conditions to position a particle. So in here we will have, so we have, for example, here this particle that is at a given position with a given velocity. So we just draw it in this way, and this is another one here. Okay, so something that is very interesting and is going to be also emphasized in the next class is that this situation, when you have like trajectories that cross, this actually is not allowed for to be analyzed in a phase plane, in a phase portrait. So these conditions, when you have like non-unique solutions, this is something also somehow we discussed in the second class. For example, what happened at this point? Okay, at this point you have a particle with a given position and a given velocity, but in this case this is somehow suggesting me that it can have two different futures. Okay, this particle can go in this direction or in this direction. So this is going to be already an ill-posed problem, and that's why we don't want to have intersections in the phase plane. Okay, no intersections are allowed in the phase plane, the phase portrait. So this is what we will see actually often, that we have just a given condition, in this case position and velocity, and this is completely defines the future. Okay, there is no this ambiguity of dual futures or something like that. Okay, there is just one way, one line, so we don't have intersections in the phase portrait. Okay, so as I just said before, then we can convert this system into a two-dimensional system, each dimension represented by a first order differential equation. Okay, let's plot this thing. Let's see how it looks like. Okay, so we start and we just need an initial condition to analyze, an initial point. So just allow me to do this. So we will start with just point a point in here. Now we have to be or to know where this particle is going to move. Okay, so we need the rate of change of x and rate of change of v. Now if we are in here, let's look at this equation. It means that we have a velocity that is 0. Okay, because this is velocity in here is 0. And we have x that is positive. So based on these equations, I already know that at this moment I'm not allowing changes along x. So if I have a change in the particle, which I will have, it's going to be only related to changes in v. So it means that I can define like a line. Okay, so this is going to be the change. So now the question is going to be moving upwards or downwards, and that actually depends on the sign of x. Right now we have a sign of x that is positive, therefore this whole relation is going to be negative. And right now then I'm knowing where I'm actually heading at. So let me just put this with black here. So this is going to be the arrow. Okay, and what is a phase plane, a phase portrait? We have to fill every single point in the domain with arrows. We just have done one, but we don't need to do all this analysis for every single point. That would be impossible. That would be infinite. We just need like some characteristic points, maybe 4, 5, 6, and then we will be able to actually understand the whole thing. Okay, let's go now and have this point in here. Now we will have something which is actually the contrary. I have x is equal to 0, so I'm not allowing changes in v. I only allow changes in x. Okay, now which direction? Here v is negative. Okay, therefore if I have a change in x, it's gonna be in to the negative direction, so I mean to the left. And so on. Okay, so following the same analysis, I will be able to point this one that is going to be upwards and this one that is going to be to the right. Okay, so this is how these 4 points is giving us some hints. Now let's pick a point in here. Let's call it maybe 1, 1. Okay, so in this case it means that we allow changes both in x and in v, so it's going to be a little bit more complicated. So let me just put here, this is in yellow. So v is positive, therefore I have a change in x that is positive, and here x is positive, therefore I have a rate of change of v that is negative. Okay, so I have something like this, and you just sum the two vectors and you get something like this. So basically you can do the same thing for all points. And if you keep doing this, you realize that this is actually a circle. Now if you go and do the same thing for another value of x, then you will have, maybe you will have stronger lines, but again it's gonna be a circle. And this is actually how things will look like. Then if you want to do it in a more schematic way, then you will say, okay, well, just draw the coordinates. So x, v, and then just draw circles. So this is gonna be, you will just see in the next slide, this is gonna be called a center. So depending on where you are standing, you will just go in circles forever. So we can have here a direction if you want to point the direction of rotation. And remember that these will never, these trajectories will never intersect. Let's go now to a very interesting example. Here we have again a linear system and a 2 times 2 matrix, and we will draw different phase portraits which correspond to different values of A. So you will see that changing A already changes a lot how these phase portraits look like. So we will consider three values for A. We'll consider A equal to -1, A equal to 0, and A equal to 1. Okay? So in the class, normally I do a contest and all the several groups and all this. So now it's not possible. So I will change the strategy. I will just draw this thing. I will explain it. And in the class, so in the part of this flipped classroom, when we talk about these slides, I will somehow try to recreate this virtually, okay? So that you actually participate in plotting this. Maybe with different values of A, maybe with different little differences in the matrix A. But let's right now start with this, okay? So the first thing we have to do is to just draw the coordinates. Okay, voila. So the coordinates have been drawn. And let's start with this one in here. And let's start with the same strategy as before. So we just have to just choose a point and see what happens. Okay. So in here, we can do this point. So some of you maybe have some trouble with this notation, so you can actually just recreate again the equations based on this. So you say, okay, this is x dot equal x minus x, and y dot equal minus y. So like this, things might be simpler to understand, and you can say the same thing. So in here, for example, y is 0 and x is non-zero, is positive. Therefore here the change in x dot is gonna be negative. I will just put blue, and I don't have any change in y, because in this case y is 0. Now if I place myself in here, it's going to be somehow the contrary. So now I'm pointing in this direction. Okay, so you can actually go and do the other 4, and you already have somehow the shape of how this looks like. Now if you again do the same example as before, you just put something like in here, so like a 1 1 coordinate, then you will have a vector. So you have this pointing in this one pointing in this direction, and then you just have this. Now when you just fill the whole thing, so you will see that you have another one in here, another one in here, another one in here, and you just can as I showed before, just put this in a more schematic way, just with lines in the face portrait, and you will see that all lines, they approaches the origin 0, okay, like this. So this is commonly known as the star. You can just plot the arrows, okay. Now the next one is also pretty interesting, because I will show you here. This is x with white. So x dot is equal to what? Yeah, to 0. And y dot is equal to minus y. So what does it mean here? That if you stand in any point that you choose, anyone, there is no allow change in x. So all is gonna be, every single point will go downwards, every single of them. And if you put it in here, they will go upwards, okay, because of the negative signs in y. So all these arrows will be like this, all of them. They do not intersect. Now when you just draw this in the face plane with the trajectory, with the lines, there will be just lines that are vertical, like this, pointing to the x-axis. Now let's think about something maybe we haven't mentioned. You can just think this to be an attractor, okay, because every single point in the domain will evolve following a trajectory that points to this origin, okay, in this case following always like straight lines. So this is one fixed point, which is an attractor. Now in here, every single trajectory is vertical, pointing to the x-axis, but then they are actually going to different places, so they are not following, or they are not pointing to a given single point, like in this case. So this is actually a line that is full of fixed points, infinite amount of fixed points, okay. So in this case is qualitatively very different from this one. Okay, now let's finish with this one. This is x dot equal x, y dot equal minus y. Again, we do the same thing. We put our selection here, in here, in here, in here. And now let's draw some arrows. So what do you think is gonna happen? It's gonna move, if I choose this point, it's going to move to the right or to the left? Yeah, very good. I heard some of you already saying to the right, to the right. Okay, this is not the good one. This is okay, because here x is positive. Now if we go, we just follow this negative axis here. This is to the opposite side, and this one actually are the same as in this case. Okay, it didn't change, so they are pointing inwards. Like this, okay. And this is a very interesting fixed point. So again, here we have only one fixed point, but this fixed point is actually not an attractor, even though you have here a set of arrows pointing inwards, okay. So you can just you are able to somehow discern what is going to happen if I put a point here. So everything every trajectory right now is just like a combination of the trajectories in this axis. So here you see this trajectory, it was like a combination of this axis with this axis, in here as well, but now it's gonna be slightly different. So this is gonna follow this direction, like it goes and then just deviates. Okay, goes and deviates like this. Voila, so we have this other kind of face portrait. So you see that just a little change in the value of A gives completely different results and a completely different system. Now, we already gave a name to this. This is going to be an attractor. This is going to be a complete line of fixed points. And this is going to be, wait for it, a saddle. So this is a saddle, this point in here, okay? It means that you have one direction that is attracting and one direction that is repelling. Okay, what else we can actually note in here, which is gonna be much more simple. So we could, as we did, just going with the equations minus x minus y and think what's gonna happen. But somehow, well, at some point it will get maybe not super efficient. So what we can do is to look at the matrix in here and already know the so-called eigendirections and eigenvalues. So this is something we'll just follow in the next slides, actually during the entire class. So if you see here, this matrix is diagonal, therefore we already know the eigenvalues, which is our -1 and -1. And the eigendirections, again because it's diagonal, we know that the eigendirections are x and y. So in this case, let me just plot it in here below in a small version of it. So I have here this eigendirection with a negative eigenvalue, so it means that this is going to be an attractor. The other one is here with a negative eigenvalue, is going to be an attractor, and you get somehow the same thing. And then you just say what happens in the next the other points is just a linear combination of the two. Okay, and so on. So here is the same idea and the same idea. It's just considering eigenvalues associated with given eigendirections. Okay, this is somehow the motivation. Don't worry, you don't understand this right now. We will just go through it in the rest of the class. So we just showed 3 different face portraits with different like asymptotic behavior. One of them were actually just pointing to a given point, which was an attractor. Some of them just was this line of fixed points, and the other one was not an attractor, not a repeller. Actually, it was a saddle, because it was attracting from one side and repelling from the other. So we can actually have this concept of the stability to be able to refer to those cases. And we have somehow 2 groups. We can say that a given system, well, a given fixed point is attracting or not attracting. Okay, and in another way of looking at things, we can say that this is Lyapunov stable or not Lyapunov stable. So what is Lyapunov stable? So imagine you are in a given, so you have here a given fixed point, for example in here at the origin, and you place yourself super close to this fixed point okay? So imagine an epsilon distance if you want. Now, and then you just let the time goes. If the point remains in the vicinity, so you can just say, for example, that I have a radius, so a circle with radius epsilon around this point. If the point remains in this vicinity, it means that the fixed point is Lyapunov stable. If this point goes away, this is not Lyapunov stable. Okay? So, the first case that you can have is, for example, this one. You have a fixed point that is attracting and also Lyapunov stable. And this is actually somehow obvious because you can just select any kind of attractor as the one we just showed, and there will be Lyapunov stable because they're actually converging to the fixed point. And the other one is just a repeller, so you just have the opposite situation, okay? But this is something that not many people think about, this case. So you have a case that is not attracting but is Lyapunov stable. This is actually it could be very strange, but actually we just saw it. Let me just give you 5 seconds and think about the 3 cases we just showed before with these 3 different values of A. Which of these 3 cases fulfill this situation? I think most of you are right. So the case with the line of fixed points. So we have here this line of fixed points. Imagine there are many, they are actually together, no? They are infinite, an infinite amount. Now let's assume we will study this fixed point in here. Then we just select like a little radius around this fixed point. And then we just select our initial somehow particle that is very close to this fixed point, a distance epsilon. What happens is you just let it go, so you just advance in time, so this particle will just move in here, okay? So it will converge to another fixed point that is next to it. So actually the system itself is not attracting. So if we are talking about that fixed point, I'm just pointing in here. So this fixed point is actually not attracting in this case for this particle, but it's Lyapunov stable because the particle remains in this neighborhood. Okay, now let's go to another case that is also peculiar. This is attracting, but it's not Lyapunov stable. And we already saw it. Actually, yeah, we already saw it. Think, okay, we have fixed points that are repellers. So the repeller doesn't fulfill this. Attractors do not fulfill this. Saddles do not fulfill this because saddles, they are not attracting. Okay, what else do we have? We have half stable points. So again, we have this example, and imagine we have a half stable point like this. So you again put this radius around this fixed point, and if you have here you put a point in here, you will have you have an attractor, so you will just reach to this point. If you are in here, you are just going away. So in that sense, this half stable point behaves as an attractor. Okay, if you consider, of course, this, you can call it Basanov attraction. But it's also not Lyapunov stable because there are points in this domain, this circle we just did here. There are points within this domain where points just fly away. Okay, so this is not Lyapunov stable. This point they will just go away. So we have already talked about, again, attractors, repellers, saddles. So we want to know in a more, let's say, rigorous way to classify them. When to know that something is a repeller, an attractor, and so on. Okay, let's start just showing here the problem of interest with, in this case, a 2 times 2 matrix and the vector x. One of the most important takeaway messages of a calculus class is to know that a linear system of equations, like this one, have solutions of this shape. So you can have the eigenvectors of this matrix, which are easily to compute because we have a small matrix, and a given solution, so a particular solution, will be just the one given by the eigenvector with the corresponding multiplication of a lambda t, where lambda is the eigenvalue. Okay, so this is super important, and you will see that when you actually base your solution on this, so the actual solution is going to be a linear combination of this. It is then possible to introduce this solution into the problem of interest in here, and then you will realize that you will get this somehow equation. You just cancel out the exponential terms, and then you get the eigenvalue problem. So this is very nice because now you know why this V is called the eigenvectors of A and lambda the eigenvalues. So we want to find the eigenvalues and the eigenvectors of A. So if you remember from your linear algebra class, you can do this. You can just reorganize the equation and find the determinant of A minus identity matrix multiplied by lambda. So this is how it looks like, and then you just apply the determinant operation. So this times this minus bc, so here, and then you just reorganize the terms a bit to make it more, let's say, manageable. So the final equation we want is just a quadratic equation on lambda, and we have defined two very important quantities that will accompany us from now on, is the so-called determinant. So actually determinant, it means the delta here, which is AD minus BC, and the other one is tau, which is the trace, so A plus D. So the quadratic formula can give us this solution, lambda 1, lambda 2, so with trace and determinant of A. And if you haven't done it yet, so this is an opportunity when you actually, it's a good idea to have this already memorized. Okay, so this is a short formula, and maybe you already know it from school. Okay, so this is a good idea to have it in mind. So as I pointed out before, then we have just a linear combination of two particular solutions, x1, x2. So this is given the x1, this is the x2, and just a linear combination with some coefficients c1 and c2. how do we find these coefficients C1 and C2? Yeah, exactly. This is just depending on the initial condition. So depending on the initial condition, which actually you need two initial conditions because now we are in a second order differential equation, a two-dimensional case, then we will find based on these two initial conditions C1 and C2, and that's all. So this chart is extremely famous when you have a linear system and you want to characterize the corresponding fixed point in terms of unstable nodes, stable nodes or attractors, saddles, and we will see later centers, spirals, and so on. So there are like a, let's say, a zoology, somehow like a jungle of things that just based tau and delta actually already know what is going to be the behavior. Remember, just maybe just to clarify, in a linear system, how many fixed points do we have? We have one fixed point only because we have, let's say, one root of this fx equation. So that's why this matrix is only associated with one fixed point, and this fixed point has these features, okay, saddle, unstable node, centers, all this. I do not want that you learn this by memory because it will be like a PT. So let's derive this thing by ourselves, okay? So we need just this somehow delimiters. So let's start from the beginning. So we have two eigenvalues given by this and by this. And the first case is, okay, let's assume that delta is positive. Then which of these two actually is true? This one or this one? So it means that this one is going to be here larger or here is going to be smaller. So if you go and think a bit, you realize that this is actually the good one. Just think in terms of having minus t squared larger than t squared minus 4 delta. So if you think about this, then you can see that this term is smaller than this one. Therefore, this is actually the one that is going to be true. Okay, so we have that. Now that we have this, let's have another question. We have lambda 1 and lambda 2. Are they from different signs or the same sign? Okay, just remember tau is larger than this. So if, let's assume, for example, if tau is a positive value and is larger than this, it means that this quantity is positive and this quantity is also positive. Okay, and you can analyze it in the same way if you have a negative value for tau. So basically it says that we have this situation. So lambda 1 and lambda 2, they have to have the same signs. Okay, that we know that they have the same signs. Okay, now we analyze the other case when delta is negative. So basically it's the opposite as before, so this is gonna be the one that is true. So this is the good one. And in that situation, what is happening with the lambdas? It's the opposite. So this term is larger, or let's put it in this example, this is larger than this one. Therefore, if this is positive, at the end the whole expression here is going to be negative. So this is going to be negative and this is going to be positive. and you can analyze it in the same way if you have a tau that is negative. So it means that lambda 1 and lambda 2 have different signs when delta is negative. So we have so far this classification, and we want to then put a name to that. So let's start with this. We said that delta is positive, so this one, and at the end what we are interested is in this somehow outcome. So it means that in this case we have two eigendirections, and both of them are pointing to the same line. So we have here either attractors or repellers. Okay, just as an observation, I shouldn't forget, we are assuming this situation. What does it mean that we are assuming this situation? It means that this has to be a positive number, which means that the square root of this positive number is real. So it cannot be complex. So in this case, we have analyzing lambdas that are real. What happens now if we have a tau that is positive? It means that lambda 1 and lambda 2, they will be both positive. So, and if we have two eigendirections being positive, we will have a repeller. So maybe to clarify this, I will just put just a quick plot in here. Remember this. One eigendirection is positive, so it's like moving out from the fixed point. This is also positive. So at the end of the day here we have a repeller. Okay, so an unstable node. In the other case we will have an attractor, so a stable node. Okay, what happens with these ones in here? Yeah, they have one eigendirection that is repelling and one eigendirection that is attracting. Therefore we have saddles in these two cases. Okay, what happened now that we have this case? Yeah, we have actually a negative value of this. This is going to be an imaginary term, and therefore the lambda is a complex number. So the question now is, this happens for both cases? Well, actually not, because you have here a minus sign. So we have a lambda that is negative. It means that this is going to be positive, and therefore we will have a real number. So in order to have complex numbers, we need that delta is positive. So I really suggest that this analysis we just did is the one to be somehow attentive to while assigning a role or a stability to a given fixed point. So given tau and delta, you just can know what is going to happen. So you just saw in here that we didn't use memory, we just use analysis, and that's what results in this plot, okay, in this chart. So given delta, so for lambda and tau, and this condition, then we can just establish the role of the fixed points. Okay, so let's start with this example and find out what is going to be the solution, and the corresponding fixed point is going to be what? Repeller, attractor, saddle. And we are given in addition a initial condition. So what we have to do, the first thing we have to do is just to actually just write down the matrix. What is the matrix A in this case? Yep, we have 1, 1, 4, minus 2. What is the second thing we have to do? So we just saw the importance of knowing this delta and tau, so the trace and the determinant. So what is the determinant of A in this case? Minus 2 minus 4 is equal to minus 6, and the trace is 1 minus 2 is equal to minus 1. Okay, so from this one we could already know the kind of fixed point. Yeah, now that we know a saddle, we want to still know the precise solution. That we need the values of lambda, so we just replace it in here. Lambda is equal to minus 1 plus minus 1 to the square, so this is going to be 1 minus 4 minus 6, okay, over 2. So this is equal to minus 1 plus minus 6, 4, 24, so this is 25 over 2, and this is minus 1 plus minus 5 over 2. Okay, so we have two solutions already, 2 and minus 3. So we have the eigenvalues. Now we need the eigenvectors. Okay, so most of the time I realize that this is somehow forgotten, so how to find the eigenvectors. So just let's do it quickly. So we have the matrix A equal to then A 1 4 1 minus 2, and then we will need just to introduce this minus lambda. We do A minus lambda 1, so identity, A minus lambda 2, identity. Now 1 minus 2 minus 2 minus 2, here 2, no, 4 1, and in here we have 1 minus 2 plus 3 plus 3 1 4, then we have minus 1 1 4 minus 4, and so like this, and 4 1 4 1. So just a note by passing, so you just realize that you are doing the things correctly, because now you have the rows are linearly dependent. It can be clearly seen. Okay, this row is linearly dependent to this one, and this one to this one. Actually this is the same. So let's do the eigenvectors now. We can just get any of the rows, so we have minus 1 1 multiplied by v1 v2, and the other one is gonna be 4 1 v1 v2, and this is equal to 0. Okay, then we have that v1 is equal to v2, and here that 4v1 is equal to minus v2. So we have now the eigenvectors. So here we can just assign a value to v1, so we can say that the eigenvector is going to be, let's say, 1 1, and in here the eigenvector is going to be 1 minus 4. Okay, now we have the eigenvalues and the eigenvectors, as you see here. What do we do with that? First, just let me know which of these two cases is the right one. Think. So v1 in here is 1 1, so you just put yourself here. 1 in x, you have 1 in y. In here is gonna be like the opposite. It's gonna be like 1 minus 1. So it means that this is already like wrong. And now if we go to the v2, it's the same. We have 1 in x minus 4 in y. So this one looks correct. This one actually looks then wrong because it's the opposite. And yes, so this should be like this. Now we have the eigendirections. This is the important part in here. We have the eigendirections, and for each eigendirection there is associated an eigenvalue. So if we put a given point on the eigendirection, so if we just choose a solution to be in here, so what is going to happen? So the solution is going to be just exactly given by the particular solution lambda 1 x1, where this is x1. And here you already see what is lambda 1, the growth rate. Exactly, remember the idea of conceptualizing this kind of system. So this is going to be the growth rate, and it's positive. It means that it's growing, that is going away, that is diverging. So it means that the eigendirection has to point in this way. If we go to the second one, now what is standing in v2, what is going to happen with the evolution of the particle in time? So again, this is going to be the solution, and this is going to be the growth rate. In here the growth rate is negative, so it means it's gonna decay. It's gonna have an attractive behavior over this eigendirection. And then we have this. So if you happen to have a point exactly on this line, then eventually you will approach the center asymptotically. Now, in a more realistic case, you are not ever over these eigendirections, you are just in between. Therefore, the solution is a linear combination, as is shown in here. See, here we can have just any trajectory, just as I showed you just in the next slide. So if we point in here, we will just go to the origin and then deviate. The same in here. So we already know how the phase portrait looks like. We have the big picture. But let's concentrate now on the question we were asked, because what we just did is qualitative. You just see that we can actually know the solution for any kind of initial condition. Okay, we already know that if we are in here, we will go towards here when time goes to infinity, Depending if we're in this initial condition, we go somewhere else. But this is the initial condition that was asked in the question. So we can just somehow, like in a very schematic way, show the solution. So this is gonna be a point 2 minus 3, so somewhere in here. Okay, so based on this point, we will know that the solution is gonna just go to the right and evolve, also growing in y. So this is gonna be the behavior of the solution. We can still use the normal mathematical tools to know the answer. So this is what I just showed. So we can just, as done before, we can have the initial condition given by this equation. So because remember that the solution is exponential lambda t times the eigenvector. If t is 0, then exponential lambda t is equal to 1. Therefore we have something like this, and this is just a system of two equations. This is the corresponding unknown, and you can just have the corresponding coefficients that satisfy the solution for that initial condition. Then you can have actually the solution to be like this. If we just plot, we just get this behavior, and it's very similar to the one we retrieved qualitatively. So we have a point 2 minus 3, it goes upwards and then go to the right to the infinite. We can actually, this is the phase portrait, so we have our axis x, axis in y, but we can also somehow split the solution in terms of time. So in that sense, we will need to split the vector, so x ball in x and y, and then we will just see here the evolution in time of x and the evolution in time of y. Okay, so now we will talk about spirals and centers. So things become more interesting because now solutions will be allowed to oscillate, and this is actually a new big, like large horizon that opens to us. So what do we need to have this oscillatory behavior? So basically here in this slide nothing changes, so it's exactly the same as we had before. The only difference is that now we have this new somehow condition coming into the game, which is this. You remember we had this definition of lambda, you can see in here, and then the square root. So if this actually is happening, it means that this term is going to be imaginary, and then lambda is going to be complex. So we can have this kind of structure. Okay, so the lambdas, they will be complex conjugate, and just by replacing the value we just showed you before into this lambda in here and in here, we can actually find through the Euler formula just the oscillations we were looking for. So most of the time in actual problems, for example acoustics, when you have this sort of complex solutions, then you just take the real part. This is the one that actually interests us, and then you can have, in this case, such a behavior. So you have a cosinus, so you start like this, imagine you have this cosinus, but now you will have somehow like a bound imposed to this cosinus. So this is gonna call like the envelope. So you can see it in here. So this envelope, which is somehow governed by the real part of the eigenvalue, is the one that will tell us if the oscillation is gonna grow or decay. Or in other words, it's gonna tell us if the fixed point associated with these eigenvalues is stable or not. So in this case, we can recognize that this is a decaying function, therefore this is the actual situation we have. Well, but how these kind of oscillations they look in the phase portrait? So let me just have the solution split. So what I meant when I say solution split is we have the actual solution is going to be C1, so our constant, multiplied by lambda t a e omega t and the eigenvector 1 plus C2 e lambda t a minus omega t eigenvector 2. Okay, and this is the bold, and therefore this is composed by x and y, and this is just a given example. Okay, that x happens to be following this shape and y this shape. So if they are out of phase, so you see that cosinus and sinus, they are out of phase of pi over 2, then we will have like a center. But now we have alpha, and this alpha is the same for both. In this case is negative, which means we have an exponential decay, and in that sense the center that we had becomes a spiral that is actually stable because it's convergent to the fixed point. Okay, this is like a sort of trivia game. So you have this x and y. Now in this example we have both are sinus, but we have a phase that, let's say, we don't know, and we have an alpha that is very close to 0. So which of these two phase portraits represent this situation? Okay, so who is up to the left? Who is in favor of the right one? Okay, and the actual answer is, voila, this one. Okay, basically because the thing I just told you before, when we don't have any exponential decay or growth, if alpha is 0, it means that we will have a perfect circle or a perfect ellipsoid depending on the value of c. But something that we don't know is that if alpha is just tiny, it's very close to 0, then it means that the orbit will somehow be almost the same, so it will change in amplitude a bit every rotation. In here, for example, we see that at every rotation it changes a lot. So this one eventually will also go to 0, but after many rotations. In here there is not the case. So it means that this case should be related with an alpha that is negative and somehow very different from 0. Okay? Okay, let's now forget about alpha. So we know that this alpha in here and this alpha in here are different. So just remember what I just told you before, in 3 slides before, and now we assume that this c is equal to pi over 2. So in that case, which of these two examples is the good one? Okay. Again, this one. So what I told you before is, now we know that this alpha is different from this one, so this is something, is an statement of the problem. But now we see that the phase here is pi over 2, and if this phase and this phase are, or if the two solutions x, y are out of phase by p over 2, it means that we will have something that is very close to a circle. Now, if this changes, for example, if this is 0, and so the x and y, they have the same phase, you will have a line, like you have a particle going in a line like this. So instead of rotating like this, it's gonna be like in a line like this. And anything in between pi over 2 and 0 is like somehow like a ellipse that is, and a spiral that is twisted, okay, a bit, and that's why we have this one. So I find this is interesting, just to see how to visualize already like these kind of solutions in the phase portrait. Now I will introduce to you a very nice model of love, actually given in the book of Strogatz, and I like it a lot, so that's why I will tell it just half of the story, because I want that we do it together, okay? Otherwise it's not going to be fun if I just talk by myself alone. But let me just introduce the whole thing. We have a constant or a variable called Romeo's love. So when this is positive, it means that Romeo's love for Juliet, okay, is positive. There is Romeo's love, so it exists. If this is negative, it means that the love is not anymore love, but is hate. So Romeo's hate for Juliet is actually present. And Juliet is also the same thing. So you have love for positive J and hate for negative J. And this is Juliet's of love is towards Romeo. So this is this. Now that we know this, we will introduce this in a ODE. So the first assumption is that A and B, or let's say the condition is A, B is equal to Z, A is larger than 0. They are positive numbers. And we have here the rate of change of the love of Romeo for Juliet, and the rate of change of the love of Juliet towards Romeo. And this is the constant. So the first thing is, this is a typical way of understanding love. So this kind of equation is something that, at least in our teenager years, we see constantly, and I hate it when it happens, because I mean, just go and see what does it mean. How, if this is positive, this increases. If this is negative, this increases. You get it already? Okay, this is all what I want to say here, because otherwise it's not going to be fun if I keep talking alone. We will recover this in the lecture, so on Thursday. So this is the basic way of how love may work in our society, unfortunately, but that you can actually build your own model. So I assume some of you already have girlfriends, so it would be nice to tell me, maybe for the next class, just prepare a model. How does it work for you? If this is representative of your relationship with your girlfriend, or you propose another model. So again, for the next class, I want you to tell me what this model means. So in addition, we can have two other love models. So we have something maybe more complete, more hard to analyze, and this one. So right now, what I want to do, I will divide you in groups. So this is going to be, I will tell you this next Thursday. so before this class, and each of you will draw me the face portrait for each model. Okay, so the answers are there already. For example, some of you will model this one, and the idea is that you demonstrate me that this is the actual face portrait you obtain. But the most important part, apart from the mathematical results, is you to tell me what does it mean, okay, in terms of this love model. So there are 4 different situations. We can have 4 groups for doing this. You have 1 week to carry out this modeling and tell me the complexity of love. And of course, if you don't agree with these models, they are too simplistic and your relationship with your girlfriend is much more complex than this, feel free, just derive something and let us know. Okay, so the class finishes here, and we will continue next week. Then we will just use what we learned today to analyze nonlinear ODEs in 2 dimensions. Okay, bye bye.